Hello everyone, welcome to part 2 of like a midterm review. It's going to be um, units from 1 to 8, and it's just like a combination of FRQ and MCQ questions. So see here we have MCQ here, and then we're going to have FRQ down here, more FRQ, and then more MCQ, FRQ, and then MCQ. But yeah, so let's go right in. Alright, so an elastic cord of unstretched total length of 16 centimeters and a cross-sectional area of 2.0 times 10 to the negative 6 meters squared is held horizontally by two smooth pins at a distance of 8.0 apart. The cord obeys Hooke's law. The load of mass 0.4 kg is suspended centrally on the cord. The angle between the two sides of the cord supporting the load is 60 degrees. What is the Young modulus of the cord material? Okay, so Young modulus is going to be stress over strain, which is I think is like stress over strain. And then you have to know these formulas. So stress is going to be F over area, or F is the force acting on the strain, and then A is a cross-sectional area, and the strain is the change in X over the original length of X, basically. So let's try and plug in everything that we know. So the force, well, first off, this mass is going at an angle, right? So there's two tensions like that, and they both pull upwards. So T, let's say this is the magnitude of it, cosine of 30, which is half this angle here. So you get the vertical component basically. Cosine of 30, and then there's two of those because there's two sides, is equal to 0.40 multiplied by 9.81. And if you divide this, you get T is equal to 2.26 or like 272655. Let's do that first. So that is basically the force that's like acting upon the string. So it's going to be 2.2655 over the cross-sectional area, which is going to be 2.0 times 10 to the negative 6 over the change in X, which is the final minus initial. The final in this case is going to be 24 centimeters, simply because we have an equilateral triangle, right? So it's 3 times 8.0 minus 16 centimeters, because we have 8 centimeters here and it's twice around, right? Divided by the original length, which is 16.0 centimeters. And then yeah, we just kind of like divide this out. So 2.2655 divided by 2e to the negative 6 times 16 divided by 8. And then you get 2.2265500. So 1, 2. So there's 6 zeros. Then we round to 2 six figs, and then thus our answer is C. A trolley of mass 600 kilograms is initially at point P on a slope at height of 80 meters above ground level as shown. The trolley is released from rest and moves along the slope, first coming to rest at point Q at height h above the ground. The total distance PQ moved by the trolley along the slope is 1.5 kilometers. a constant resistive force of 300 newtons opposes the motion of the trolley on the slope. What is H? Okay. So we have energy up here and we have energy here. So recall that the gravitational potential energy is mg delta h, right? So it's going to be 600 times 9.81, and then 80 minus h basically. It's going to be equal to what? So we don't know what this is supposed to be equal to, but if we look at the diagram, they give us this information of 1.5 kilometers per hour and 300 newtons. And you should make the connection that this should be equal to the work done by friction or resistive forces in this case. So this question mark is not going to be here. It's going to be 300 multiplied by 1.5 times 1,000, because you have to convert 1.5 kilometers to meters. And then you have to solve out this little thingamajiggy. Yeah, I don't think there's a function on the calculator that solves. Oh wait, there is one. So if you have the TI-30X Pro, you can hit second and then num solve, and then you can just enter in your equation. Where are the variables though? Here? Okay. And then 300 multiplied by 1.5 multiplied by 1,000. And then you get H is equal to 3.547, which is about 3.5 meters, which is A. We're gonna skip this because it's the same thing here. A hollow plastic sphere is attached to one end of the bar. The sphere is partially submerged in water, and the bar is attached to a fixed vertical support by a pivot P, as shown in figure 3.1. The sphere has the weight of 0.3 newtons. The distance from P to the center of gravity of the sphere is 0.29 meters. Assume that the weight of the bar is negligible. The variation of the force applied to the spring with compression X is shown. Calculate the spring constant K. Alright, so to calculate the spring constant of K, you have to know that the K is newtons over meters basically. And this is in millimeters. This is kind of like you have to notice this during the exam. So in this case, K is actually going to be the slope of this line. Let's take this dot and then draw a triangle from here. This seems the easiest straight line I know. So then it becomes 12.5 newtons, the change, of course, divided by 0.006 meters. If you do that, you get a K constant about 2100. Calculate the elastic potential energy of the compressed spring. So EP is equal to 1/2 kx squared, where x is equal to the full extension, or the extension that happens basically. So we just plug in the values. We can see that it stops around the second mark here. This is 22.5. So this is about 21. So, wait. Yeah, I'm doing the wrong thing. Sorry. We're looking at this one here. So 10 millimeters is the same thing as 1 centimeter, right? So it's going to be 0.01 squared. And this is going to be 0.105, but we round to 2 sig figs, so it's going to be 0.11. When the sphere moves from position shown in 3.1 to the position shown in figure 3.2, the upthrust on the sphere does work. Assume the resistive forces are negligible. Explain why the work done by the upthrust is not equal to the gain in elastic potential energy. Okay, so it doesn't really show you, but basically, I think what I was trying to say is like, your sphere moves up, right? And why is this upthrust not equal to elastic potential energy? Well, it's because the sphere is also gaining energy, but the energy that it gains is gaining gravitational potential energy. Oop. So basically it's asking like where the missing energy is, right? Your next question. A solid cylinder is lifted out of oil by a wire attached to a motor. Figure 5.1 shows the two different positions X and Y of the cylinder during the lifting process. As shown, the motor is fixed to an overhead beam. The cylinder has a cross-sectional area of this, length of this, and weight of that. The density of the oil is 940. Throughout the lifting process, the cylinder moves vertically upwards with a constant velocity of 0.02. The viscous force of the oil acting on the cylinder is negligible. Okay, so I had to search this up, Lookie, the first time, but basically the viscous force of the oil is just like the friction of it. So you know how like air resistance is like you're running into molecules of like air, and that makes you slow down. This is kind of like the same thing, except for instead of air, it's oil. Like you're running into the oil particles, but you just don't want to like assume that it slows it down. But yeah. So A says calculate the density of the cylinder. So density is equal to mass times velocity. Oh my god, I can't believe I said that. No, it's not that. It's mass over volume, sorry. So the mass in this case, we look at the problem and see look for the mass, and they don't give us a mass. But they do give us a weight, and remember that weight is equal to mg, right? So they give us 560 is equal to mass times the acceleration of gravity. Do that real quick. You get about 57.0846 divided by the volume. The volume is the cross-sectional area multiplied by the length. And it turns out that the units are pretty good. Like they're all in meters, they're all in like newtons, so it's like pretty solid, and we don't have to convert our units. And then we got our density is 260 kg meters cubed. Okay, for the cylinder at position X, show that the upthrust due to the oil is 200 newtons. So this is on the formula sheet, I think. So the upthrust is equal to rho times g times volume displaced. So this is equal to, U is equal to rho, and rho in this case refers to the liquid. So it's 940, which is given here, times the gravity constant, 9.81, times the volume, And the volume is just the volume of the thing. So it's going to be 0.018 multiplied by 1.2. And you should get 200, about 200 if you round. Which is to be shown. Calculate for the moving cylinder at position X, the tension in the wire. Okay, so we have to draw a free body diagram here. So notice that there's a force starting here, that's gravity. We have a tension here, and we also have an upthrust force, right? So in this case, it's going to be like Fg is equal to T plus U. We know this is true because we're moving at a constant velocity, right? So these forces should cancel out. Our force down is going to be 560 newtons, which is just the weight. The tension is what we're solving for, and the upthrust is what we just solved for in part B. So then T is equal to 360 newtons right there, and we're done. Two isolated spheres have masses of 2.0 kg and 4.0 kg. The spheres collide and then move apart. During the collision, the 2.0 kilogram of mass has an average acceleration of 8.0 meters per second squared. What is the average acceleration of the 4.0 mass? Okay, so we have to use Newton's second law where F equals to ma, right? We have to know that the force acting on both the objects have to be the same. So if we take the first part, F is equal to 2.0 multiplied by the acceleration, 8.0, which is equal to 16 newtons, right? 16 newtons of force. So if we look for the 4.0 kg, we get 16 newtons of force multiplied by 4.0 kilograms multiplied by the acceleration. In this case, we're going to simply divide by 4, and then we get that the acceleration is about 4 meters per second squared. All right, next question. A mass is placed on a frictionless slope inclined at 30 degrees to the horizontal. The mass is then released. What is its acceleration down the slope? So let's draw a diagram first. Ooh, I can still draw, that's crazy. So we have our little block here, right? And as a force, that's not good. Force going down, this is going to be mg. And then we have this, right? This angle here is also 60. So we're moving down the slope at a sine of 30. Multiplied by our magnitude mg. So it's going to be m times 9.81 times sine of 30, which is equal to 1/2. So it's going to be 4.9 m. And I think, wait, there's something wrong. Oops. Oh my god, I just saw the news of the shooting. How tragic. And I don't mean that sarcastically. But, yeah. So, this is the force of it going down, right? So, recall that in the previous problem too, F equals to ma, right? We know our force is going to be 4.9 m, and then that's going to be equal to ma, and then m is going to cancel out, and then we get 4.9 is equal to a. A ship of mass 8.4 times 10 to the 7th kg is approaching a harbor with speed 16.4 meters per second. By using reverse thrust, it can maintain a constant stopping force of 920,000 newtons. Damn. How long will it take to stop? Well, so we know that force is equal to mass times acceleration, right? If we looky here, we know they give us the force, which is going to be 920,000 newtons is equal to the mass, 8.4 times 10 to the 7th kg, multiplied by the acceleration. If you plug that in your calculator, we get the acceleration is about 0.01, and we know that it's going in the other direction basically. So we use the two-body equation of v equals u plus at. V is 0, 16.0 minus 0.011 times t. T is equal to 1490 seconds, which is 24.8 minutes, which is approximately 25 minutes, which is C. A car of mass 850 kilograms tows a trailer in a straight line along a horizontal road as shown in figure 2.1. The car and the trailer are connected by a horizontal tow bar. The variation with time t to velocity of the car can be shown in 2.2. Calculate the distance traveled by the car from t equals 0 to t equals 10 seconds. So if we draw this here, we're looking for the area of all of this. And one thing you should know is that this is cut off here. So there's actually a large amount of area down here, basically. But if you look here, this is 9, and this is 13. And up here, it's gonna be 10. And then if we imagine that this is a trapezoid, we do base plus base, 9 plus 13, multiplied by height, and then we divide by 2. And then this is equal to 110. If you're doing calculus, I think this is much easier to visualize because you do go over like the trapezoidal rule or something, or the trapezoidal approximation for integrals. So it's basically kind of just like this. It's just geometry. If you don't know, if you can't imagine this, try splitting it like this. So then you get a triangle as well as a rectangle down here. I know it looks like a square, but it's a rectangle. Yeah. Alright, at distance 10 seconds, the resistive force acting on the car due to air resistance and friction is 510. The tension in the tow bar is 420. For the car time t equals 10 seconds. Calculate the acceleration. Let's see. Okay. I think you can choose this, no? Oh wait, no, you can't. Yeah, I think we can just choose this. So we know that acceleration, right, is equal to slope of velocity graph. Velocity time graph, I should be more specific. So we're just gonna take the slope of this, which is gonna be 13 minus 9 over 10, I think, which is gonna be equal to 0.40 meters per second squared. Yeah, I don't know why they give us this information. I think it was like they're trying to do something else. I didn't really make these questions, but I think this like information here is like kind of useless for this question, but it's probably useful for later parts, you know. It's okay. We're here now. All right. So the diagram shows two readings on a micrometer, A and B. What is the difference between the two readings? So this question is obviously like trying to see if you understand how to read a micrometer. So I actually didn't learn how to read from a micrometer in class because I was sick. So I watched a video on YouTube. And it's actually like really simple. You have to like pull it out and then screw it. And in general, I think it's pretty intuitive. And if you forget, just watch a video like some guy explaining it like for an engineering video. It's really straightforward. So basically what you do is that you take this part here, you take the tick mark, the part of the tick mark that you can actually see, and that's like I think that's like your pre-decimal place, or it's like your 10th digit in this case. It's like your 10th digit, right? So if we look over here, our 5 is here. That means that each of these big ticks here is going to be 1. Each of these small ticks is going to be 0.5, right? So in this case, it's going to be like 1.5. And then we have to add whatever is on the side here, basically. And you want to look where it's perpendicular. And in this case, it's going to be 1112. So plus 0.112, which is equal to 1.62. And if we do the same thing here, we do 5, 10, 11, 12, 13. So 13 points, whatever we add here, 46, plus 0.46. And if we add this, oops, not add, subtract it, sorry. We get D, I think. Yeah, we get D. A person calculates the potential difference across a wire using the measurements shown. Which of the measured quantities has the greatest contribution to the percentage uncertainty in the calculated potential difference? Okay. So you kind of have to know basically like how to calculate potential difference. In this case, it's going to be like VIR, I think. And you have to calculate this R, right? And okay, wait, I think I'm kind of tripping. But basically, you do have to use volume in this case. I'm kind of confused why this is not cubed or something. Well, basically, it's like V is equal to the current, which is like A. And it's like the resistivity of the thing, right? D. And then you have to divide by like the meter, the diameter, or the volume, basically. Basically, in general, this is like has a power of 1. This is squared. This is 1, and this is also 1, basically. I kind of like botched the explanation, but basically you do have to find the volume of the wire, and since they only give you the diameter, you have to square it to get the cross-sectional area, and then you have to multiply by the length to get the actual volume. And then they're looking for the percentage uncertainty, right? So it's going to be like the uncertainty divided by the value, and then that's your percentage uncertainty. So for A, it's going to be 0.1. For B, it's going to be 0.1 divided by 0.8. And you have to multiply by 2 because there's two, you have to square it. So you have to multiply the percentage uncertainty by 2. For C, it's 5 divided by 150, and you get 0.033. And for D, 0.2 divided by 1.6, it's going to be 0.125. In this case, it's going to be B. And I'll try to search it up, like, real quick. Let's see. K, Q over R. Where's the VIR, right? So we have the V equals A and then the ohms, right? But they give us ohms and ohms meters, so you do have to like divide by a certain like value of these two. I'm pretty confident. Okay, so it shows here, if you look at R is equal to rho times L over A, where A should be the what is it, the cross-sectional area, and if you do this out, this should cancel out the units, but basically like that's how you do it. I don't know, my intuition just said when I like initially did this problem that the diameter it's probably related to like the cross-sectional area, so this is probably gonna be squared, and that's like the only one that kind of made sense anyway. But yeah, so that's gonna be it. If you have any questions, just leave a comment below. Make sure to like the video and subscribe. Share it with your friends. As you can see, I'm doing this at a very fine hour, but I'm still here. I know I'm kind of slow, but you know, better late than never, right? You guys have a good night.